Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to start talking about something called vector-valued functions. So this is really what the entire chapter 13 is all about. And really today you're going to start to see why I wanted to talk about some of those quadratic and hyperbolic surfaces now, because this is really the first place that we're going to start to use them. I never really understood why they're in that last chapter, but anyways. So a vector-valued function, very important things, very useful in tons of like motion, mechanics, engineering, physics, stuff like that. But they are functions, and their domain is the set of all real numbers, and the range is a set of vectors. So they're basically things where you plug in some number, and then you get out a vector, or vectors really. This picture right here is basically the best idea. A lot of times the way we write these two are, so we'll do like R of t, and the t is there to kind of remind you, it's almost like a time stamp. So you could have this be what the vector valued like function ends up looking like. And you get that by plugging in at like r of -1, you can see it just barely there. You get a vector that takes you right there. And then r of 0, vector that takes you there. R of 1 takes you there. And so if you think like all real numbers, you start to plug in all these little intermediary values, and you actually get like a curve. You can get like things like this, like a helix. You can get weird things like kind of the wireframe structure of like a cone or something. A lot of like, a lot of literally like force problems, like with orbits, we use vector-valued functions to describe them. If you're an engineer and you're doing some sort of like spring system, this one might be really useful. But basically it's, they're kind of 1D curves, but drawn typically in 3D. Technically, you could draw them in really any dimension, but a lot of times we just use them in 3D. And they basically are built just out of like an infinite amount of these vectors, like this, where you're just sort of connecting, typically we think from the origin out to some spot, and then we just have like a connection of all these points to get these kind of curves like that. So these are two examples. I just noticed this should have a comma. So they are written like a vector is, where it's like some, here it's like a 3D vector, but you have these t's in here, and so you plug in a t and you get a different vector out, right? You can take like limits of them. So you can also write it this way, where I have the ijk structure. But basically, like, let me just kind of show two. So with this, if I have r of 1, let's say, right, I'm going to get the vector 1. I need a little more room, I think. 1, and then I'll get natural log of 2, and then I would get 1. So that's just like the vector I get out from plugging in this t equals 1. So for domain, because these curves like this are not defined always everywhere. They have like domains. So on this one, you can plug anything you want into the first thing, right? You can take the cube of any value. But for like this part, we want 3 minus t to be greater than 0, because that's where the log is well defined. So we would get t is less than 3 for that. And then for the square root, right, we want t to be greater than or equal to 0, because we're talking about like real numbers here. And so the domain for this one, it's got to work like everywhere, right? So it works everywhere here. You have to be less than 3 here and greater than or equal to 0 here. So these two things dictate it. So the domain on this problem for this vector valued function would just be starting from 0 and going up to 3. So it's only going to graph between those t values. You're never going to be able to plug in like t equals 4 or something. This is actually probably a good time to talk about this too. So I hate to change things on you because you're probably used to this, but I don't really ever write that way of an interval, and nor does anyone else in the math community typically. The way we actually write that is like that. So these are actually, technically equal, but in my experience, only people in the US do this. This is much more the standard way that we write interval notation for this. The people in the US just sometimes want to change things and make their own notations up, but they're not always the best notations. The issue with this is if they were both open parentheses, like if you was the open interval 0 to 3, this interval looks just like a point. And so long before we adopted this, people were doing this. And basically, if you want a parenthesis, you just do a square bracket pointing out. So it avoids the confusion of the point part. So if you wanted an open interval 0 to 3, you would just do 0, 3, like that. I didn't really see this till college, but it's time we basically switch you guys over to. So in college, you'll probably see this way more than you're going to see this. At least I hope you do, because that's the correct way to do it. Everywhere else in the world, they do it that way. So anyways, I'll know what you mean if you do this, but that's really the way you should do it. So you can take limits of these things. If you take the limit of vector valued function, it's just the idea like as you approach 0, you come in from both sides here, you're just sort of wondering what like vector do you basically get close to. So if you plug in, if you want to take the limit of vector value function, you literally just take it of each little part right here. So the first part, you literally can just plug in 0 and you're going to get 1. And then similarly, if you plug it in here, you're going to get 0, right? This is that famous limit from like Calc 1. So the limit as t goes to 0 of sine t over t. Over t. That's the one where you use L'Hopital's. So you take like the derivative of top and bottom, right? And so it's really the same as, I haven't written a limit in a little bit. Limit as t goes to 0 of now cosine of t over 1, right? And now you can just do like direct substitution and you can get 1. So this means that as you do this limit, as you approach 0 on this vector valued function, you're approaching the vector 1, 0, 1. Basically just the idea that as you, like if you think of this picture, as you come into t equals 0, the vector that we just got was 1, 0, 1. That's the idea. So they're just, they look like curves. You plug in different t values and you get out vectors. These are just other examples of them. This is like a torus, like a donut looking thing, and there's actually a very famous, this is related to a physics problem that has to do with black holes, and there's actually like a problem about how an object would sort of move into it, and you can model it with one of these vector valued functions. A lot of wireframe CGI work is actually done with vector valued functions too, so maybe you encode the surface of something with a wireframe like vector valued function like this down here, and then the computer does some magic. I don't really know how it all works, but I know that they use vector valued functions. we're actually going to do a problem in a bit where I look at the intersection between two objects, and that can be a vector valued function. This is actually a very famous one over here. This is the vector valued function t squared, t cubed. I think they call it the twisted cubic. It's kind of cool looking. Yeah, you can do like weird knots and things like this. This is something actually that we're going to study way down the line in chapter 16, but it's something called a line integral. And okay, that's totally misspelled and also horrible handwriting. Line integral. Okay, better. But basically the line integral is going to almost be just the idea of finding the area under some sort of space curve. So you could have this red like curve through space, and then if we find the area under it, like the signed area here, like below the curve and above the xy plane down here, that's actually like a type of integral called a line integral. Really, I hate the name of it, and it should be called a curve integral because we basically build it off of like these weird space curves and things. But that's a ways away. That's like March or something. Okay. So I just wanted to show you like a really kind of straightforward example. So if you actually can just make an analogy to parametric with these things. So we can think of a like vector valued function as just here cosine t and then sine t, just a 2D base curve. And it's really just parametric, right? Like if you graph this, for everything 0 to 2 pi for t, right, you're going to start right here, and you're just going to get that circle. If you graph it for 0 to pi, right, still start here, and you just end right there. But really, parametric is a vector valued function. It's like, we're now just saying, like, we're going to write this like that, but you're used to this from, like, BC Calc and stuff. It's just parametric. Plug in different t's, get different x's and y's, right? And that's just how the unit circle works. Basically, the difference is I want you to think of it as like at different t values, we're getting different vectors that take me out to the, to the curve. So, like, to be specific with one, right? Like if I do, that one right there, that would be t equals 0, right? And t equals 0 would give you that point. It outputs the vector, the green vector right there, that gets you onto that part of the unit circle. So like the last question, if we just make a 3D problem now where it's cosine, sine, and then we just have t, I don't think it's too hard to see that the thing we would get is basically this last problem right here, but like pulled out of the plane, the xy plane, right? So you would actually just get a spiral like this. That just, if we only graph it from negative 2 pi to 2 pi, it's going to start like below the xy plane down here. And then t equals 0 would actually be right at the origin. That'd be the 0 vector, right? So it's an easy one to write. R of 0 would equal the 0 vector. But then, it's just going to continue kind of moving up as you plug in different t values, right? Like pi is pi up in the z, pi over 2. That's weird. I should have these flipped, but whatever. It would basically be a spiral, right? So I think this is a good problem to start kind of getting your brain seeing how these things work. And sometimes we write it that way, and sometimes we just write it like cosine t, sine t, and t. So when I see this, my brain just thinks like a spiral. just like this picture. All right. So a lot of times these show up when we do, we need to find like a curve of intersection. So maybe the curve of intersection models some like physical thing that we want a function of, and be able to, plug into a computer nicely with like parametric. And so if we get a vector valued function, we can always get like, parametric, like x equals this, y equals this, z equals this. So it's a very useful problem to be able to do something like this. So we got a cylinder, x squared plus y squared equals 1, and it's just infinite in the z. And then we got a plane, y plus z equals 2. And the question is, basically find a vector valued function which represents, this like curve of intersection right there. So kind of like a elliptical sort of region. All right, so you just need to find basically parametric x and y's that work for these equations right here. This one, we could definitely use cosine t squared plus sine t squared equals 1. We know that works. So basically I know x can be cosine, and I know y can be sine. And then we have this other equation right here. And if I know y, which is sine t, I can plug that in to get what z should be. Right? So z then can be 2 minus sine t. And so if you want to model that vector valued function that's a curve of intersection here, you just take x, which is the cosine t, y, which is sine t, and then z, which is 2 minus sine t. And I'll show you in class, but you can actually plot these things in Math 3D, and it's kind of fun because you get these cool like curves and stuff. But I think I'll actually, I'll pull this example up in class again, just so you see that you actually can get that as exactly the curve of intersection between like infinite cylinder and this plane right here. All right, so this problem is actually another one that I think I want to pull up in Math 3D sometime to show you like it really, like how it works. But so we have a vector valued function right here, which is like this curve. And then we have one of these like bowls, these like paraboloid things, those surfaces we saw like last class. And this one is like opening down the z-axis. And the question is, at what points, like what t values, does this curve intersect this surface? So the way I would think about this, you have, like over here, if I kind of pull it out, it's like parametric. It's saying x is t, nope, not y, that's a k there. Z is 2t minus t squared. So what I can do is I can, and actually I should actually also add y equals 0, right? So that is the parametric for this vector valued function right there, right? And so what I can just do is I can take these x, y's, and z's and plug them in over here. So if I substitute in to this, I basically get 2t minus t squared equals t squared plus 0 squared, right? And then I can just solve this thing for t. So let's see, we got 2t would then equal 2t squared. So I'm just going to get this quadratic. And I'm going to, we could also divide by 2, I guess. T squared minus t. I'm going to factor out a t. Okay. And then the way you would get 0 here, right, is if t equals 0 then, or t equals 1. And so what I can't really show you super well here, but if you go and get the vector, like you go plug those t values in up here, you would get for t equals 1, you get the vector 0, 0, 0. And then for t equals 0, you get 0, 0, 0. T equals 1, you're going to get 1, 0, 1. So you just get that by plugging in up here. And the part that I can't show you super well, but this one's probably not so hard to see, but that is actually the 0 vector right there. And then there's another point. So this is like the t equals 0, and then this is the t equals 1, but there really is the vector coming out that is 1, 0, 1. And I'll pull this up on Math 3D and kind of be able to spin this thing around and show you it a little bit better. But yeah, those are the two vectors that sort of mark the intersection of this vector valued function and this surface. All right, so this is just another good question to kind of get you to get comfortable with vector valued functions. So I want to show that the curve with parametric equations t cos t, t sine t, and z equals t actually just lives on the cone z squared. That's what I was going to put in here. The cone z squared equals x squared plus y squared. And I'm going to use this to kind of sketch it, but I just screenshotted it right here. So basically what is actually happening is you sort of get this vector valued function is a infinite cone shape. And it's going to go up and down forever and ever and ever. And just kind of like the last question, if you wanted to show that it lives on that cone forever and ever and ever, you can just take your parametric or your vector valued function, and you basically just substitute in and see that you get an equation that's just true for all t. So if you plug in z, which is t, you get t squared equals x is t squared, or x squared will be t squared cos squared. Y squared is t squared sine squared. And then, let's see, I would take a t squared out. And then you have the trig identity, where you can make this 1. And really, we can just stop there, right? Because no matter what t you have, you have a true equation there, right? So that proves that this red curve is always living on that cone right there. Yeah. And the cone looks kind of funny, I was going to say, because it looks like it's cut off or something. But really, this cone is infinite. It's just the way that the 3D graphing program I used does it. But I don't want you to think that that cone stops there. It really does continue forever and ever and ever. I kind of did this actually so I could get you to see that the red is actually like cone shaped. So I just want to do another curve of intersection kind of problem. I kind of feel like this is one of the more important things that we sort of do with vector valued functions a lot of times. And there's also a weird surface here that I haven't showed you before, but if you take the surface z equals x times y, it looks like this, and it's kind of like it is a saddle surface, but it's like a weird one. So it's kind of like a planar saddle surface because it doesn't have like the parabolic x squared structure that the other one had. So if you graph it in like a 3D graphing program, it does look like planar, but it's like a bent sort of twisted plane that has like saddle structure to it. I can show it in class too if anyone wants. But if you want to also try the traces, you could see how you could get this a little bit better. If you do like the projections onto the different planes, I think you'll see that it does look like a saddle kind of surface. but planar-like. So really I want to make sure that we can do the curve of intersection between that and this, which is a cylinder that again is just going to open up in the z direction and go forever and ever and ever. But this one has the circular cylinder, and the radius of it is the square root of 4, which is 2, right? So the parametric that is going to represent the curve of intersection here, it has to satisfy this equation. And in order to do that, you can't just take cos t plus sine t now, and because that doesn't equal 4, right? Or cos squared, I guess, sine squared. So you can't take x as cos and y as sine, because this would be like 1 equals 4. So I don't think it's super hard to see. If you want to get a 4 instead of a 1, right, just stick 2's in front, and then if you square that whole thing, then it really will equal 4, right? Because you'll get a 4 in both terms here that you could factor out, and then 4 equals 4. So you know that like x is 2 cos t and y is 2 sine t. And then you just need to get z. And so you can do what we kind of did before, where we now can just set we know z equals xy. And so if we just do 2 cos t, 2 sine t, we get the z is 4 cos t sine t. And there's a trig identity that I do think it's probably the second most important trig identity, I would say, after sine squared plus cosine squared. And that is the double angle for sine. This one just shows up a lot. So that is equal to this. So this is a very good trig identity to know. So if you wanted, you could use that and simplify this a little bit. So 4 cos t sine t would just be 2 of those sine 2t's. So instead of writing the 4 cos t sine t, I might just sub that in to my vector valued function. So the final answer that I would write down for my vector valued function would be just 2 cos t, 2 sine t, and then 2 sine 2t. And if you plot this in Math 3D, you plot this in Math 3D, and you plot this in Math 3D, I promise you'll see that they actually do truly line up perfectly as the curve of intersection. All right, so there was one more problem I wanted to do, but this video is running a little longer than I want, so I probably won't be able to really do it out. But a lot of the, physics problems and things with vector valued functions kind of feel like this, where you might model 2 orbits, like the orbit of an asteroid and the orbit of Earth with a vector valued function. And then you might want to know, do those particles or just things collide? And basically it's just a bunch of algebra to, do a system of equations and see if they actually are going to end up in the same, the same vector at the same time. And I guess I can show this part probably really quick, and then in probably a future video I'll show the other one. But do the particles collide? Well, then you would need t in the first one to equal 1 plus 2t, and that would mean t equals -1. But then if you sub into the next, the y equations, then -1 squared would have to equal 1 plus 6 times -1. And that would mean 1 equals -5, which doesn't work. So no. So it's not too hard to see that they don't collide, but it's a little harder to see that do they intersect or not. And the answer is actually yes, but I think I'll show it in another one because it takes a little more work to do that.